So in this video, we're going to talk about how to draw stereoisomers. So we already have talked about different kinds of isomers like constitutional isomers, geometric isomers, enantiomer, and all that, the chirality. We have talked about all that. So now the very last portion of this particular chapter is where we would learn how to draw different kind of stereoisomers for a complex compound. So I'm going to show you two examples today, which is quite complicated, and after that there will be homework, but I do believe this particular video will help you to draw any kinds of complex, with different types of ligand attached with it. So I'll start with a simple one. Let's say Ma3B3. The detail, you should check my lecture notes for the detail for different types of, complex compound. I'll pick up the example Ma3B3. M is the metal and A and B is the ligand. So how can you draw this particular molecule? Okay, you can think about it something like this. Let's say cobalt, NH3 and Cl3. You can consider that as a kind of model of that type of complex molecule. Okay, so how can you draw this? So right now, remember, I'm trying to draw the stereoisomers, not the constitutional one, the stereoisomers. So for that, as you all know, the stereoisomers really the changes in the position. So how can we write down the same molecule in a different way? So this is an octahedral molecule. As you can see, there are 6 ligands, so that is an octahedral molecule. So for octahedral molecule, you have the square plane, and then one ligand is above the plane, and one ligand is below the plane. So if you want to consider, that's kind of a plane. So I put this dot dot, that's kind of plane. All right, this is kind of plane. One is above the plane and one is below the plane. If you consider this is the plane, then one is this side and another is the opposite side. Okay, so this is octahedral scenario. And Ma3B3, you can draw it in two different ways. One is you write all the A in the plane. All right, so in this particular case, you have put all the A in that plane and the B is right here. Okay, that's one way of doing it. And let me do it another way. And in that case, I would, let me change it a little bit to have a little bit more space. So over here, this is the second way of drawing it. You may be wondering what's the difference. If you pay attention, you will see this particular structure, A, and A, they are essentially a face, okay, a one part of the face. So we call it FAC isomer, facial isomer. It's kind of, holding one side of it's on the face of the octahedron. If you want to consider there's octahedron in there, it's kind of, on one side. That makes it FAC. And the MAR, the way we are characterizing this particular molecule is you have A, and A. It's part of the same plane, and this plane dissects the molecule in half. So if you consider this particular plane, B is on the top, another B is at the bottom. So it's literally cutting the molecule in half. So this particular scenario is what we call MAR, when you have all 3 ligands part of the same plane. Okay, so this is MAR and this is FAC. And these are the two different ways. The next, what I would like to draw is a little bit more complicated. It's also octahedral molecule, Ma3BCD. The question is, how can you draw the different stereoisomer? Remember, the moment you move the position of the ligand, it becomes a very different complex. The electronic structure is different. If you basically, take a visible spectroscopy of these two molecules, you would see they're different. So they are different molecules. So it's important to know how many different isomer you can get based on the same chemical formula. So Ma3BCD, it's again an octahedral. And the easy way of starting is, let's say I'll start with FAC. You can draw, it's kind of similar, MA3, but no more B3. You have now 3 different ligands, B, C, and D, 3 different ligands, and also A. So essentially you have 4 different ligands. So let me draw my octahedral scheme, okay? And let me draw A, and A. So this is my FAC because it's basically covering the face of the octahedron, one side, okay? So this is A, and then I have B, B, and B. So this is going to be my, so that's basically FAC. Now you have C and D, so I will change that to C and D. So this is going to be my 1 isomer. Let me talk about few other one. So we can start with something like MAR in this particular case. So let's say I have M. Okay, and so it's basically a MAR kind of a configuration, correct? So you have this plane right here. And now where are you going to put B, C, and D? See, you can do it in multiple different ways. You can put B and C as trans and D is cis. So the next picture, you can basically, instead of B and C, you can have D and C, right? So you can draw it in a different way. Still, you are keeping the position of the A constant, and you are only changing the position of, let's say, C and D you are interchanging. So in this particular case, all right, so in this particular scenario, you have B and C as the trans, B, C trans. In this case, you have B and D trans. So they are very 2 different molecules. The third one, well, you already guessed it, I'm pretty sure. So here I still have A, just like before. I have B, C, I have B and D. So the next will be C and D. And this is my B. So here C and D is trans. So all I'm doing here, I'm moving around the ligand. Okay, the complication in this particular practice is that you may draw the same molecule again and again. That's why I'm showing you how to do it, where you can see the way I have drawn, they are distinctly different molecule. Because this is BC trans. Here B and D is trans and C and D is trans. So they're obviously 3 different molecules. All right. So you have 3 of them here. And you have another one here. And this particular one has an enantiomer, which means it has a chiral center. Now, we have talked about how to identify the chirality, in my lecture material already. So if you pay attention, you would see this particular molecule doesn't have any inversion symmetry or any, any plane, all right, any sigma plane. So that makes this particular molecule chiral. So if this molecule is chiral, so you can basically get a mirror image of this particular molecule, and that makes it number 5. So if this is your number 1, number 2, number 3, number 4, and the number 5 is the mirror image of, if you consider that's the mirror here, then you can basically draw the molecule in this way. So it's basically inverted now, okay? So it's basically inverted, as you can see over here. Okay, so this A is in this side and this is inverted through the mirror plane. So this is a chiral molecule. It has its own enantiomer. So altogether you have 5 stereoisomer for this particular complex molecule. All right, so I hope it's helpful. Thank you all.